And of course, the elephant in the room, though, when you're going to talk about Copernicus, you kind of have to talk about the fact that it sure doesn't feel like the Earth's moving.
So in the sophomore math tutorial here, we spend about a semester on Ptolemy. And then in the spring semester, we take up Copernicus and then move to Kepler.
Yeah.
So all three of these thinkers are looking at the question of the heavenly bodies and how they move and providing mathematical arguments. And in certain cases, other sorts of arguments to say something about the nature of the heavens and the order of the heavenly bodies and the way in which they move around. So what strikes you about Copernicus to kick things off here?
Yeah. Copernicus is, he's writing, almost 1,500 years after Ptolemy's writing. And so Ptolemy's view of the geocentric universe, Earth-centered universe, holds sway basically continuously for that time period. And then Copernicus, this Polish canon Catholic, proposes a revolutionary approach to thinking about the heavens. In some respects, counterintuitive insofar as it implies that the Earth is not only revolving around the sun, but rotating on its axis once every 24 hours. And yet, his theory, in certain important ways, is not that different. I mean, from Ptolemy, at least in this sense. It seems like he takes all of Ptolemy's observations, which were relatively good and extensive at the time, and he says, if you look at it all a little bit differently, you can actually set the Earth in motion, as I said, rotating on its axis and revolving around the sun annually. And that puts a whole new light on all the same observations. He didn't discover or observe something that Ptolemy hadn't observed, that Ptolemy couldn't explain, and say, okay, we need a new theory. He just says, let's take those same observations and put the Earth in motion. And then it seems like you've got a whole new theory. Geometrically, it looks kind of different. And it also suggests a very different way of thinking about our experience of the Earth as immobile, right?
Yeah, it is really interesting that I think often the students are expecting Copernicus to have had access to some kind of observation, or perhaps even technology, telescopes or something like that, that just gives you some kind of greater insight into what's actually happening, and that's behind the big shift.
Yeah.
But it's not the case, as you say.
Yeah, telescopes are like about 70 years later that they start being pointed at the stars, and with Galileo most famously. Yeah.
Now, you mentioned the 1,500 years of the Ptolemaic universe in position, and that encompasses the entire Christian and medieval era up to that point too. Yeah. So we have Copernicus at the outset, very aware of the controversial nature of his claim. Yeah. And doesn't he even address one of his opening prefaces to the Holy
dedication.
Father?
Yeah, Paul III. Yeah.
Right. So he's aware of the fact that there will be contention surrounding his views. Yeah. Do you think that that's just a matter of is he covering his bases there, or what's?
It seems like there's probably some of that, but I think it's right historically that there was a previous pope. So this is Paul III, and there was a Clement the maybe seventh who had heard of Copernicus's ideas, and Copernicus had sort of publicized a first draft of these things. And that pope had heard about it and was very approving and encouraged Copernicus to go forward with it. So it wasn't just a fear that the church is going to go after me, right, that motivated him to write that dedicatory letter to the current pontiff in 1543. But certainly you're right, a sense that this is a very different view from what most everyone else has proposed, and there will probably be factions lining up against him. It's not yet like in Galileo's day, 70 or so years later, in which, or maybe more like 90 years later, where the church itself is deeply suspicious of what Galileo is proposing, right, and even silences him at one point, 2 points, you might argue. At this point, the church sort of didn't think this was a threat to the faith, right? I think that's right, judging from these two popes. I don't think that the pope that he dedicated the letter to was hostile to the Copernican idea either.
Yeah, for our students, they have in mind just to take one example, Dante in sophomore seminar, for whom you get this wonderful tour through the entirety of the cosmos, Inferno, Purgatorio, and Paradiso, and in some way it's all predicated on a Ptolemaic view of the cosmos.
Yeah,
it's geocentric.
It's just you got the Earth there, and everything is concentric circles going around it.
Right. Yeah. And in turn, Dante himself relies heavily on Aquinas, who relies on Aristotle, for whom some of his proof for the first mover at least touches on something like a Ptolemaic universe, or seems to involve it in its account.
It's explicit in Aristotle.
Yeah. So there's a lot that's at stake, aside from just a sort of interesting mathematical model as to how the universe might run.
Yeah, I think that's right. What you said just reminded me of something that I said in the last podcast about the center of the universe. So you remember in Dante, at the center of the earth is Satan, right? That's the deepest part of hell. That's sort of a further confirmation of the idea that the center of the universe was not a place of great dignity, right? Whereas that's at least the stereotype of why we all liked the geocentric hypothesis back in days of yore, right? Because we liked being at the center of things.
Right.
Whereas actually the philosophers and the theologians' estimation of a center of the universe is actually where all the crummy stuff settles out, right? The dross of the universe. And so naturally, that's the deepest part of hell, and that's naturally also where Satan is suffering.
That's a great point. Yeah. So Copernicus moves fairly quickly to point out some of the real problems he sees in his predecessors. You might call it the Ptolemaic account generally, but there were other thinkers more close to Copernicus's own day. And he brings up the fact, among others, one of the things he brings up is the fact that what Ptolemy gives us when it comes to a view of the whole cosmos is something like a monstrosity. He says that it's as though you were to create a person, a man, taking an arm from over here and a head from there and feet from somewhere else, and you end up with almost like a Frankensteinian type of creature. You have thoughts on what he means by saying that?
Yeah, I think that's because, if I understand Copernicus right, he's looking at the fact that Ptolemy had a theory for each individual heavenly body. And by that, I don't mean the outer stars, but by each of the planets and the moon, the sun. So he had a special theory to explain mathematically what produces the orbit of the moon. Another different theory to explain what produces the movement of Venus and Sun and Jupiter and Saturn, etc. And each of them are similar insofar as they all involve deference. So circles, eccentric deference, eccentric to the Earth, right? And an epicycle, a star moving on an epicycle on that deference. So a circle rotating on a circle. That carry each of the stars. So the different theories for the different heavenly bodies are similar, but he never tries to put them together and make a unified whole out of it. I think that's in part because he has no judgment of the distances, no way to judge the distance to the heavenly bodies. They all seem just pretty dang far away, right? So he can't say, okay, well, the sun is closer to us than Mars is. He just sort of speculates that would be fitting, that the sun would be closer. But he doesn't have any real evidence, any way of measuring distances or triangulation or something like that.
And I guess it's also the case that for these different planetary models, he could go one route, that is to say, by placing an epicycle on an eccentric deferent, or it could be explained by not making the deferent eccentric to the Earth, but rather placing an epicycle on another epicycle, maybe, right? So you come across this several times in Ptolemy, that there could be different geometrical ways of explaining
that are equivalent.
That are equivalent in terms of the appearances, but he ends up going with one over the other, maybe on account of a kind of simplicity or something. So I wonder if that's in his mind too, cautioning him from wanting to just lay out, okay, here's what the whole would look like.
Right, I think that's right. And he's got a smaller work called the Planetary Hypothesis, where he does try to put the orbits together, but just based on a sense of what would be fitting. When he's doing things, you might say scientifically, or at least mathematically, and not positing too many hypotheses in the Almagest, right, the main work. There he just keeps everything free floating, right? And that's one of Copernicus's virtues, is he can put them together, right? There's certain things, for example, in the case of the inner planets, Venus and Mercury, he calls them inner. And we would call them inner as well for different reasons. But Mercury and Venus seem to stay within a certain fixed number of degrees of the sun. And so that's just a brute fact that Ptolemy doesn't have any real explanation for, right? What he calls the average longitudinal motion of Venus or Mercury is the same as the sun's longitudinal motion. And it's really not too big of a leap to say if Venus is staying within a fixed number of degrees of the sun, and so is Mercury, maybe the sun is just at the center of the orbit of Venus or Mercury.
Yeah.
Right? So whereas Ptolemy's just saying there's this orbit for the sun and there's this other orbit for Venus on an epicycle, right? But the sun always seems to stay lined up within the orbit, in a sense, right? Within the apparent orbit. What if it's within the physical orbit? That is, you just bring the orbits together, right?
Yeah. So for Ptolemy, you could walk away from the whole thing just thinking, well, yeah, it happens coincidentally that the sun and Venus move at similar enough speeds to where Venus's movements back and forth will always stay fairly close to the sun. But the sun could be incredibly far away from Venus. Whereas, Copernicus is going to want to actually give an explanation for why Venus and the sun are always within a certain range from each other.
Yeah, that's right.
By positing that the sun is at the center of Venus's orbit.
Yeah, that's right. And Mercury's, right? Those, for what it's worth, too, we could mention that this is something we've all kind of observed insofar as if you've recognized Venus in the morning sky or the night sky, right? You call it a morning star or an evening star precisely because it's always very close to the position of the sun, right? So most people have actually sort of observed this fact about Venus in particular, that it stays within a certain number of degrees. That's why at certain times of the year it'll rise before the sun. You call it a morning star, right? And other times of the year it'll set after the sun, and we call it an evening star. Right?
Yeah.
They call them all stars because they figure they're all self-illuminating planets or a kind of star.
Yeah. So it's a very interesting proposal in terms of the kind of weight that it carries. So it's not like, as we've said, Copernicus is not bringing some new dramatic observation to the table.
Yeah.
He's saying, look, if you simply shift your way of thinking about things such that the sun becomes the center of the orbits, then something makes sense. I can give a reason for something that for the last 1,500 years was just a matter of coincidence.
Yeah.
And it's amazing to see how in the classroom, say, the students will almost without even thinking about it, just go for that, right? They'll see, oh, well, of course, that this makes sense. So it's very interesting that there's just the intelligibility of reality, the fact that we can see reasons for things, that we can give an account of something, that in itself is a reason for accepting a particular thinker's model of reality rather than another's.
It's a clue. Yeah. We tend to think if it's a theory's a good scientific theory, it has to make new predictions, right? It has to say, okay, if my theory is right, then when we observe such and such, we'll see this that we didn't see before. And that old theory didn't make that prediction. Copernicus doesn't do that. He simply presents the theory as a unified whole, right? Not a monstrosity, right? Such that he can put all the orbits together and then explain the fact that the longitudinal motion of the inner planets is the same as the mean motion of the sun. And for the outer planets, there's a even more complicated coincidence where the longitudinal motion plus something he calls the anomalistic motion is equal to the mean motion of the sun again. That's based on the observation that the planets seem to do their retrograde motion when they're at opposition from the sun. So if the sun's setting over there, right, that's when the outer planets will be doing their backing up and then racing forward again.
Yes.
And that becomes absolutely necessary if those outer planets are actually going around the sun, right? Because that's just it's a side effect of the fact that the Earth is rotating around the sun, while, say, Mars is also rotating around the sun a little bit slower, right? Such that the mean motion of the sun, which is actually the Earth for Copernicus, is actually going to be equal to these two motions, the longitudinal and the anomalistic.
Yeah, so that's really key, is that what was, for Ptolemy, the mean motion of the sun ends up being almost like this grand, it's like a clock.
Yeah.
It's like a standard for time or for motion, right? But that becomes, for Copernicus, as you're saying, that becomes actually the mean motion of the Earth.
Yeah.
Right? Because it's us that's doing the moving around the sun, not the sun that's doing that motion around us. And so when we're in between the sun and, say, an outer planet, then we have to end up seeing the kind of phenomenon that for Ptolemy is simply a coincidence.
Yeah, because I think it's right that when we are, like you said, between the sun, so between the sun and the outer planet, so that's be at opposition, right? That's when the planet should seem to be going backwards to us, precisely because the outer planet's going around the sun.
Yeah.
So is the Earth, but the Earth's going faster. So you can see how the Earth this finger would appear to be going backwards, while this one's going by it, right?
Yes, that's right.
So it's absolutely necessary for a Copernican hypothesis that there be retrogradation and that it be locked into the motion of the sun. Yeah.
So the items that in Ptolemy end up being what he calls anomalies or irregularities, those are just brute facts for Ptolemy.
Yeah.
And what we want to do is just give an explanation of them, where explanation means take geometrical circular models and posit uniform motion and be able to predict where things will be at a given time.
Yeah.
Whereas for Copernicus, those anomalies, those irregularities, simply cease to be irregularities because we've and that's entirely accomplished through shifting our perspective on what's at the center and what's moving around.
Yeah, that expression, right? They're features, not bugs.
Yeah,
right.
Yeah,
They're part of what makes the theory make sense, I guess. Yeah, I think that's right. Yeah, and of course, the elephant in the room, though, when you're going to talk about Copernicus, you kind of have to talk about the fact that it sure doesn't feel like the Earth's moving, right? And if we can just talk about that for a minute, that is sort of part of the list of original arguments that Ptolemy makes at the front of the Almagest, right? Is to point out that if the Earth, if this motion, this daily motion, say, right, of the stars moving from east to west, if that was actually caused by the Earth, he does entertain the idea, right? Entertains the idea that the Earth's rotating on its axis the opposite direction, west to east. He says, but if that were the case, doesn't it seem like things will be flying off the Earth, right? Because we're spinning so fast. And we have to do a full rotation in 24 hours, right?
And he even brings up the idea that, well, maybe the air is moving with the Earth.
Yeah.
And so that might sort of keep things stable.
Holding things in place.
Yeah, he's aware of this possibility. But rejects that, because if the air was moving as quickly as the Earth was, then you'd never have clouds, for example, seeming to drift in the opposite direction. They would be carried along with the atmosphere.
Yeah, that's right. Yeah. And Copernicus addresses it by saying, well, maybe we need to think about our natural philosophy, our physics, a little differently. And he proposes the idea that maybe everything just naturally goes in circles when they're in their resting position, their natural places. Right? So if I drop this pen, right, it's just going to go straight down. But once it's down on the table, it's gonna be at a position of rest, and everything at rest rotates. Is sort of what Copernicus proposes, and Galileo will actually run with that idea as well. It's sort of like an early version of the inertia theory that Newton will propose, such that now Copernicus can say, well, the reason why isn't a constant gale force wind or something like that blowing against us as the Earth rotates towards the east, is because the wind is going with us, right? The air is going with us. Everything naturally moves in a circle around the axis or the center of the Earth. Right? So he doesn't have any real evidence for it, except insofar as the idea of inertia is starting to be entertained by people. The idea that things that are in motion will keep going in motion at a fixed speed.
Yeah. Yeah, Copernicus is fascinating because there are fundamental principles of Ptolemy's that he'll accept.
Yeah.
Not everything. So what you were just talking about is a departure.
Yeah.
Right? This idea that even in the earthly realm, well, of course, for Copernicus, the earthly realm starts to become more like the heavenly realm.
Yeah, it's hard to tell them apart.
But yeah, even in the earthly realm, circular motion is kind of natural. But he will agree with Ptolemy that we want to explain things in terms of uniform circular motion.
Yeah.
And so the idea of a physical causality is not yet present in Copernicus.
Yeah.
So especially for a first-time reader or for the students, it's conceptually difficult because when they see the sun being placed at the center of the orbits, which is Copernicus's big move, they're expecting automatically, oh, the sun is commanding things. The gravitational pull of the sun is causing things. That's right, to move around. Copernicus simply doesn't hold to that.
Yeah, no. He doesn't propose any explanation for what caused the planets, other than to say it's just natural to them. They do, and the evidence of that is they do it forever, I guess. Right? But there's that's part of what Kepler's big insight was, right? So Kepler, who comes maybe 60 years later, right? He's the one that says, I'm going to give you an astronomy based on physical causes, right? And so Kepler is famous for his three laws of planetary motion, but the thing that he's pushing in his new astronomy book, right? The subtitle of it is Astronomy Based on Causes, or something like that, through causes, physical causes. And by that he means agents, right? He's speculating about what's causing the motion of the planets. So he's a heliocentrist. He's like Copernicus, thinks everything's going around the sun, but he's proposing that, it's probably everything's going around the sun because there's something coming out of the sun that's driving the planets, right?
Yeah, because even in Copernicus, when it comes down to it, mathematically, you assemble the various planetary orbits around the sun, but their actual centers are not the sun. They're mathematical points, which are close to the sun. They're in the vicinity of the sun, but they're not the sun. And that feels very Ptolemaic, because Ptolemy has mathematical points as centers all over the place. Very far removed from a notion of physical causality. And so there's something frustrating about Copernicus in a way that you don't have with Ptolemy, because he's so close to putting everything together. And yet, on account of this need to stick with uniform circular motion, he ends up with his own, I don't know if you'd call it a monstrosity, but there's some kind of discrepancy there where you've got these different orbits all having different centers. And so even there isn't kind of a wholeness to things in the way you might hope for.
It still seems like there's something wrong. Like you must be missing something, it seems, Copernicus, right? Yeah, I guess that's right. I guess that relates to the whole idea that you saw, we didn't talk about it last time, but in Ptolemy, the idea of an equant, right? So when Ptolemy says that a planet is moving around the Earth eccentrically, so the Earth is not at the center of the circular orbit, even of the epicycle, right, or of the deferent for the epicycle. It's moving regularly, not around the Earth, which is eccentric to it, not around the geometric center of the deferent, but around another point, and there's nothing at the center of that, and that's what he just calls the equant. There's a point of regular motion. He's sweeping out equal angles and equal times, right? That has no physical significance, right, as far as Ptolemy goes. And Copernicus, like most people, really feels like that's a violation of the idea of moving in regular circular motion. But he doesn't have much of an alternative that's well worked out.
That's right.
It's really not until Kepler that you can come up with a better alternative, I think.
Yeah, because Ptolemy, so by invoking the equant, Ptolemy really does sacrifice the actual uniform motion of the planet itself. And admittedly so. Now he claims that, well, it's uniform with respect to this mathematical point. But on its given track, it's not uniform. And that's what scandalizes Copernicus. But as you say, his solution is not much of an improvement.
Yeah.
And he posits an epicycle, kind of an extra epicycle, and it has the effect of sort of squeezing in the orbit a little bit. And so you can see how the introduction of the ellipse that Kepler brings us is really so needed finally.
Yeah, right. Both the introduction of the ellipse, because you're being truer to the actual path of the planet, but also insofar as ellipses have that unusual property of having these two focal points, right? And the focal point is where the sun turns out to be, right? For Kepler, one of the foci.
I guess. Yeah. Well, I guess we should mention too, in terms of the first point you made, that Kepler does have the benefit of observations of a new sort.
Yeah.
Of a much more precise sort that the previous thinkers did not.
Yeah, he was the student or disciple, I don't know, assistant of an astronomer named Tycho Brahe, who was, I think, Dutch. At any rate, who's a heliocentrist of a sort, right? So he agrees with Ptolemy that everything should be going around the Earth, but he does sort of a partial Copernicus insofar as he puts all the orbits of the planets around the sun and then sets the sun in orbit around the Earth, right? So this semi-heliocentric hypothesis has the Earth as indirectly the center of the universe, but the immediate center of the planets, anyhow, is the path of the sun. At any rate, Tycho had this tremendous observatory on an island. I think that maybe he's from Prague. I seem to remember his island is in Prague. That he builds this observatory, and he doesn't have telescopes, but he has things that are pretty helpful for making very careful observations. And Kepler's his assistant for years, and Kepler uses those much more refined observations than you found in Ptolemy, which Copernicus did observations as well, but nothing near as much as Ptolemy did. Kepler takes these better observations, and he can give you a much more precise account of the path of the planets, in part because he can determine distances. So he can triangulate distances among things, so that he can actually get at least relative distances.
Yes.
He can tell you how far Venus is from the sun, that kind of thing. Right? So thanks to that sense of relative distance, he can actually figure out the actual path, right, and determine that they are, at least Mars, which is the one he studies the most carefully, is an ellipse.
Yeah. This isn't Mars as well part of the title of this impressive volume here, but he focuses on Mars in particular because, as it turns out, Mars has the most elliptical orbit of the planets that are accessible to these guys.
It's easier to spot it.
It's easier to spot it as an ellipse. And even there, as we mentioned in our Ptolemy conversation, it is not elliptical by much. We're still talking somewhere in the area of 98, 99%.
Yeah, fraction of a percent, I think. Yeah, I think that's right. And maybe just to complete what we were saying about the Equant, Kepler proposes, again, just based on careful observations, that it's not so much the regularity of the motion, and it's true there should be a regularity of some sort. He agrees with that that's sort of part of the nature of nature, if you will, that there'll be regularity. The regularity of the motion is not equal angles being swept out in equal times, like Ptolemy and Copernicus wanted, and seemed reasonable, but equal areas being swept out in equal times, at least if you're measuring it from one of the foci where the sun is, right? So the area, if the ellipse is like so and the sun is down here more, right, the planet's going to move much more quickly in the bottom part because it's closer to the sun, and therefore it will, to make an area here that's equal to the area up here, right, it's going to be a smaller angle when it's at apogee or aphelion, I guess you'd say, versus perihelion, near the sun.
So that's huge because you see some sort of source of uniformity in the sun. And so what's interesting about that is that there's a kind of, you might say, rehabilitation of the Equant. Because there does end up being this point that's not the geometric center, say in a circular fashion, that's the source of uniformity, but it coincides with the sun.
And it's a equality of areas
Right.
in equal times rather than angles in equal time.
Yes. Yeah.
That's right.
So for Kepler, this is a big move by way of suggesting a physical causality.
Yeah, coming from the sun. And he proposes several things and figures out how they might work, imagining a fluid that's coming out of the sun, or he calls it a species. Makes comparisons to magnets, which is in a way equally difficult to understand what the causality is there.
Yeah.
Right? But that's what he really thinks is his contribution. I don't think he's all that excited about the ellipse in the end, right? He just says, look, it's got to be an ellipse, right? And the sun's got to be at the focus. But he's trying to nail down how you would think about the planets as moving caused by something coming out of the sun and drawing them in semicircular paths, right? Quasi-circular paths, right?
Yeah, so much so that he says toward the end that once he becomes convinced that the sun is exerting some sort of causality on the planets, that he does not expect to find any kind of geometrically regular orbit.
Path, yeah.
So a circle becomes impossible.
Yeah.
On account of observations and on account of the heliocentrism and all the problems that the Ptolemaic and Copernican models introduced. But then once the circle goes out, Copernicus assumes, well, since there's physical causes at work,
Tycho. Or Kepler.
Kepler, yeah. Kepler assumes we're not going to be able to find something just kind of mathematically beautiful. That's no longer the kind of standard that's going to be operative in the science of astronomy.
Yeah.
And so it comes as a kind of shock and revelation to him that in fact these are ellipses.
Yeah.
And so
right.
so you end up getting the best of both worlds.
Yeah, right. In the end, because the next best thing to a circle is an ellipse, right? Because he entertains, right, that it's various sort of oval-shaped and puffed-shaped figures that are, because he's just trying to fit the observations to the possible geometries, right? And the ellipse is sort of, isn't that something, right?
Right.
It turns out to have that much elegance to it.
Yeah. Kepler he's an astonishing thinker. He's in some ways a lot of fun because he's extremely dramatic and poetical in his writing in a way that you don't find in Copernicus and Ptolemy.
Yeah.
He's also very autobiographical in the sense that he wants you to know about all the different paths he took and attempts he made to figure things out so that you become convinced that, look, this is a dead end over here, or this proposal over here won't work, so that what you're left with has got to be the way to go.
Yeah.
But he entertains Ptolemy and Copernicus both together throughout most of his work.
Yeah.
And it's interesting that he sees himself largely as confirming the Copernican model, but he ends up doing so much more than that because of the introduction of the physical causality of the sun.
Yeah, right. And in a way, the irony is that Isaac Newton, less than 100 years later, is going to be able to take what Kepler did and go a lot further, but at the same time be more agnostic about what the physical bodies might be that cause the motion of the orbits, right? So Newton will explain it in terms of working out this very complex and precise theory of gravitation that predicts the ellipse. But at the same time, he doesn't propose anything that's coming out of the sun, right? He's not saying that he won't propose fields even, right? Much less some sort of fluid that's emanated, right? Because it seems pretty clear that would actually get in the way, right?
Yeah.
So Newton says, I would like to find causes, but I haven't found them at the end of my principia yet, right? I've simply given you the forces, the measure of the causality of whatever the causes are, right? Yeah.
So interesting.
So it's still physics, right? Or it's still more physical than what Copernicus and Ptolemy were doing, but it's in a way more modest than what Kepler was trying to do with some of his speculations about the actual causes.
And it's also, you see in both Kepler and Newton, if anything, the mathematical side becomes intensified.
Yeah.
It's a real struggle for students typically to work through these problems. And that's also kind of wonderful to see that the introduction of the physical doesn't banish the math, the geometry, which is kind of more abstract and if you will, self-contained, but rather it involves it all the more.
Yeah, in fact, it forces you to up your game in the math, right? So Newton. So we mentioned last time how Ptolemy has to sort of work out the rudiments of trigonometry so that he can convert arcs and chords, right? Or see the relation between them. Kepler improves the calculations. I don't know if he develops the math in any substantial sense, but Newton basically invents calculus, right? Yeah. So that he can actually deal with these things in a greater level of precision. Yeah.
Yeah, it's extraordinary. Yeah. We'll have to do an episode on Galileo and Newton next.
Yeah, we should.
Yeah. Thanks, Chris.
All right. Thanks a lot, Sean.